Problems like this, with multiple masses, are quite common in physics class. When we look at this problem, we see there are 3 masses, the 2 blocks and the pulley. And they can all have kinetic energy, and they can all have forces and torques acting on them, and they can all accelerate. So let's take a look at this. When we see problems like this, there are 2 general ways they can go. One is the problem is looking for a velocity or a speed, and that's the case here. So which lens should we use if we're trying to find the speed of an object? Probably energy, because in all the kinetic energy terms in our energy equation, there's speed, and we can solve for speed typically using energy. If we were looking for forces or accelerations, then we're thinking dynamics, F equals ma, solve for an acceleration or a force. Or if you're given an acceleration and forces and we're trying to solve for something else like the masses, we would be thinking F equals ma and Newton's laws, dynamics. And we'll do that in the next video. But let's take a look at this problem. We've got the 2 masses connected by a string. M2 is attached to that spring, and it starts out at the equilibrium position of the spring. Then we pull on that string. M1 goes down the incline and ends up down here. M2 goes up and ends up here. And we hold on to it there for a second. But before we let go, we're a little worried that when we let go, M1 is going to go shooting up the incline very quickly. And we don't want that. We want it to go up the incline with less acceleration. So we push with our hand on M1, and our well-calibrated hand always pushes with a constant force, F hand. And we keep that force on M1 the whole time it's moving after we let go of it. So M1 is in this lower position. It's been pulled down the incline by a distance d. We apply our force F hand to the box, and then we release it. We keep F hand on the box, but we release it with our other hand, and M1 then starts to move up the incline back to its original position, and M2 goes down, and when it gets back to its original position, we want to know what's the velocity as it passes through the equilibrium position of the spring. This was a problem off of an exam I gave previously. So let's take a look at this problem using our energy lens, because we are looking for the speed. And that's a clue to us to use energy because it's already in the equation. One thing I like to do is to draw an interaction diagram. And we know that the spring is interacting with M2. M2 is interacting with the rope. This would be our spring force. This would be the tension in that rope. Rope 2 also interacts with the pulley. The pulley is interacting with rope 1. Rope 1 is interacting with M1. M1 is interacting with the earth 2 ways. Force of gravity, I'll put Fg1. And through a surface interaction. It's really one interaction with the surface, but we like to break it up into a normal force and a friction force. So I draw this double arrow. One side indicates the normal force, and the other side indicates kinetic friction. The Earth is also interacting with M2 through a force of gravity. And there's a hand reaching in, interacting with M1. I know the Earth is actually holding on to the end of the spring. There's some kind of a support force, or the Earth is holding on to the other end of the spring, but For our purposes, we know something's holding on to the other end of the spring. Now we want to define our system, and it's best if we can include the earth and the springs in the system. And if I just have one end of a rope in my system, then I don't include it. I treat it as an external force crossing over my system boundary. If I have both ends of the rope in the system, I include it in the system because it doesn't do anything. They are internal forces. They can't change the motion of the system. So I would define my system as being this. The ropes that are in my system, both ends of the ropes are in the system. I include those. The spring, the earth, I include those. But I have a hand reaching across. I treat that as an external force right here. I have an external force crossing my system boundary. So I'm going to have one external force doing work, and I'm going to have gravitational potential energy for my two masses because I've included the earth, and I'm going to have spring potential energy because I've included the spring in my system. So let's write out our energy equation. My initial mechanical energy plus the work done by friction plus the work done by external forces is equal to my final mechanical energy. What do I mean by mechanical energy? Well, that could be kinetic energy, gravitational potential energy, or spring potential energy. So let's start out with kinetic energy. I know that every mass in my system could have kinetic energy. I could have kinetic energy for mass 1, kinetic energy for mass 2, kinetic energy in the pulley. These are all at the beginning, the initial point in my problem. Now, mass 1 and mass 2, my boxes could go up and down. I could have UG1 and UG2 at the initial stage of my problem. The pulley is attached to the earth. It's not going up or down. I don't need a UG pulley. And I have one spring in my system, so I could have energy stored in it, U spring. If I had multiple springs in my system, I would have a U spring 1 and a U spring 2. However many springs I had, I could have a potential energy term for each spring. But I just have one. And that's all my initial mechanical energy, EI. Then I say I might have friction doing work, and actually I do in this case. I might have an external force, and I do in this case. And then I've got my final mechanical energy, and I'm going to have the exact same terms at the end that I could have had at the beginning. So I could have kinetic energies, potential energies, and those would be my final mechanical energy. What I like to do now is make what I call an energy bar chart. The energy bar chart is very helpful when you first start doing energy conservation problems. It gets your mind thinking the right way about energy, gets you thinking about what's zero, what's positive, what's negative, what has to be on each side of the equation to keep that equality. And so if you just draw a bar chart here, and this is positive, and this is 0, and this is negative, and I just go in and start filling everything in that I know. So in this case, nothing is moving at the beginning. I've got kinetic energy for mass 1 is 0, kinetic energy for mass 2 is 0, kinetic energy for the pulley is 0. Nothing is moving at the beginning. Is anything moving at the end? Yes. M2 is passing through the equilibrium position. M1 is going up the incline because they are connected. And what does that string do? It goes over a pulley and causes the pulley to turn. So all three of our masses have kinetic energy at the end of the problem. And what is kinetic energy? Always positive. So this is going to be some positive amount. This is going to be some positive amount. I don't know the relative lengths of these bars. I don't really care. What I care about is that there's kinetic energy and it's positive. And I know my equal sign is right here. This is my equal sign. So this is the left side of my equation. And this is the right side of my equation. Let's take a look at gravitational potential energy. Does M1 go up or down during this problem? Let's take a look. M1 starts at its lowest point and it goes up the incline and it ends up at a higher point. So it goes up by a distance h1 in height. M2 starts at its highest point and it goes down by a distance d. And we know what h1 is. It's the hypotenuse here, d, times the sine of the angle theta. H, in this case, is d sine theta. So if we start our potential energy 0 at the initial point for mass 1, since it's at the lowest point in the problem, if it starts at 0 and it goes up to a higher elevation, then it has to have more gravitational potential energy at the end of the problem. What's more than 0? Some positive amount. Now we could have said it's 0 at the end. If we said it was 0 at the end, then what would it have to have at the beginning? It has to have less than 0. It has to have some negative amount at the beginning. That would have been fine. But most students like to make the lowest point in the problem 0, and then we go positive from there. Mass 2 ends up at its lowest point, so we could call that our 0 for UG2 at the end of the problem. It starts out higher than that, and if it's higher, it has to have more gravitational potential energy. What's more than 0? A positive number. Our spring at the beginning of the problem is stretched. If it's stretched or compressed, doesn't matter. Doesn't matter whether it's stretched or compressed. Either way, it has energy stored in it, and spring potential energy is always positive. At the end, it's passing through, M2 is passing through the equilibrium position of the spring, so it has no energy stored in it. The spring is not stretched or compressed at the end of our problem. Do we have friction in our problem? Yes, we have one friction force acting on M1. If both masses were sliding on the surface, we'd have two friction forces we'd have to account for here, but we only have one. Work done by friction, that's going to be some negative amount of work here. And we have one external force reaching into our system, and is it doing positive work or negative work on our system? It's doing negative work. It's causing the box to slow down. It's preventing it from speeding up as much as it would if that force was not there. So you have to be careful with your signs here. Of course, if you find the work done properly, work done is a dot product, and it'll give you a negative number if the work is negative, and a positive number if the work is positive. So these, you have to be careful, could be positive or negative. Typically, friction's negative, work done. Typically, friction slows us down. Now, what do? I write out my equation. And the first thing I'm going to write out is this term right here, and that's a potential energy term for mass 2. And mass 2 starts out a distance d above its lowest point. What's next? I have spring potential energy. Spring potential energy is 1/2 k x squared, where x is the amount the spring is stretched or compressed. In this case, that's d. Now I need the work done by friction, and so I've got the friction force times the distance times the cosine of 180. I'm just going to put a minus sign here. Friction force times the distance times the cosine of 180, which is why I have a minus sign there. And now I have work done by external forces, and again I'm going to get a cosine 180, so I'm going to get a minus sign. This is F hand times the distance that it acted times the cosine of 180, which gives me the minus sign. Now I've got my kinetic energy terms. I have a 1/2 m1 v final squared, a 1/2 m2 v final squared, and I have a 1/2 I omega final squared for the pulley. And I need one more term. I've got UG1, that's M1 GH1, which I found earlier, d sine theta. I have an I here and an omega. The pulley is a solid disk, so I is 1/2 the mass of the pulley times the radius squared. And omega and v are linked together. V is equal to r omega because this velocity is the velocity of the masses. Well, that's also the velocity of the rope. And the rope goes over the rim of the pulley. And what's the tangential velocity at the rim of the pulley? It's r omega. So omega is equal to v final over r. We can plug that in. And then we can just solve for v final. F hand was given, d was given. What's our friction force? That's mu times the normal force. And the normal force, because we're on an incline, is m1g cosine theta. And once we plug those values in, we'll have one equation with one unknown, and that unknown is v final, the velocity of the two masses at the instant we're looking for.